Welcome back to another Dockies Talkies, where we put the nice in asynchronous learning. Today we're going to be talking about collisions, where we have two objects trying to occupy the same space at the same time. Now, it can be a really violent collision, like a car crash, or it could just be something gently bumping into something else. But the idea is two objects, they try to be in the same place at the same time. When they do so, they'll exert forces on each other, and then they will move differently from how they were moving before. So we want to be able to predict. A typical thing we want to ask about a collision is, what will the final velocities be? After they crash, how fast will the objects be going? Especially if we know how fast they were going before the collision. So to start thinking about this, we have two objects. They'll both be identical in mass. To keep things simple, we'll say they're going the same speed as each other, but in the opposite direction. So this guy's going 60 miles per hour, this one's going 60 miles per hour, but in the other way. They can be on the floor. We're going to keep things simple, and we're going to say we're going to ignore friction. There might be some, but we're going to ignore it for now. And they're coming in equally massed, even though I didn't draw it that way. This one's denser, I guess. And they're coming in at each other at equal but opposite velocities. When they crash into each other, we can probably predict that they will both stop dead in their tracks. Two equal objects stop each other. So both are at rest after the fact. And if we understand energy, we can say that each object had its own kinetic energy due to its motion before the collision. So the total energy before the collision is equal to the kinetic energy of the first vehicle plus the kinetic energy of the second vehicle. 1/2 mv squared plus 1/2 mv squared. We can add those together and get, just get mv squared total. I guess these should be capital M's if I'm keeping with the scheme that I started. In any case, we have some amount of total kinetic energy beforehand. Afterwards, boom, they crash and they come to a stop. And so the energy that we end up with is zero. There's no potential energy. The cars didn't go up a hill or anything like that, or there's no springs involved. And so all the kinetic energy we had to start with has vanished after the fact of the collision. We also learned that energy is conserved. So this is strange. Where did that energy go? Well, the energy's here in this big cartoon explosion cloud that I drew over here. And the energy's not completely lost. The kinetic energy that was there from the motion of the cars has been transformed into things like sound. You'll hear a big boom when they crash. There will be vibrations. There might be heat as the molecules that make up the cars get excited and start, vibrating in that sense. Or there could be deformation. The cars ain't going to look as pretty as they were before they crashed, and they've actually crumpled and, changed their shape. It takes energy to do that. It takes work to make that happen. So all of the kinetic energy we started with has been converted to sound and vibrations and heat and deformations, which are really hard to calculate. There's no simple formula like 1/2 mv squared for these kinds of things. These are difficult to calculate, and they're also difficult to measure. The sound is going to travel in all directions. And so if you have a sound meter, you're going to naturally be missing some of the sound energy that's being produced by this thing. And so you might not be able to collect it all on top of that. So energy, as awesome as a technique that it is, it doesn't really work for collisions because the forces in the collision are going to create kinds of energies that we can't easily keep track of. So these guys here can't keep track. And so energy not well suited for this sort of thing. You can talk about roller coasters going down frictionless tracks and springs all day with energy, but collisions aren't going to cut it. But we like this idea of being able to take what's happening before in a system and relate it directly to what's happening after, like we did with conservation of energy. So maybe there's something else we can examine. When we have these two things crash, they exert forces on each other. So we know that by Newton's third law, if we call this car 1 and car 2, the force of car 2 on car 1 is equal and opposite to the force of 1 on 2. So this notation isn't 21 and 12, it's literally force of object 2 on object 1 and force of object 1 on object 2. Newton's third law says that the forces they exert in the collision must be equal and opposite. Well, we know that if this is the only force acting, it's the net force. So this is third law of Newton. We can look at the second law and say, well, hey, the mass of object 1 times its acceleration is going to be equal to the mass of object 2 times its acceleration. And there's a minus sign there as well. So we've used Newton's second law to rewrite these forces of collision as ma, as per that famous Newton's second law. Acceleration can be thought of as a change in velocity over some amount of time. So now we have m1, we have change in velocity, 1 over some amount of time, is equal to m2 negative delta v2 over that same amount of time. These times have to be equal to each other. You can't have a crash happen and have object 2 be in contact with object 1 for longer than the other way around. Those times have to be equal. And since they're equal, we can get rid of them. And so now here's the cool thing. Vehicle 1 came in and crashed. It changed its velocity. Vehicle 2 also came in and crashed, and it changed its velocity. But in accordance with Newton's second and third laws, this has to be true. Whatever happened to car 1, mass times its change in velocity, car 2, if we multiply those same two quantities for that specific vehicle, we get the same equal but opposite thing. So what we have here is this negative sign indicates a loss. So we have car 2 loses some stuff, mv, whatever that is, and car 1 gains that same amount of stuff. Well, we lost some stuff. That's equal to the amount of stuff that car 1 gained, and so therefore we have another conserved quantity. Whatever this mv is, it has to be another conserved quantity that's different from energy, and this one is specifically conserved in collisions. So what is this stuff? Well, if you were paying attention to the title of this video, I assume you were, you could probably guess that this stuff is called momentum. So momentum is the product of mass times velocity. You can think of it as mass in motion is a corny way to say it, but it works. It's what it is. You take an object's mass, you multiply it by how fast it's moving, and you get its momentum, which is symbolized with the letter P. Now, I don't really get that one either. I think it has to do with, originally when they were devising this idea back in the 1700s, they wanted to call it like impetus, which is a Latin word for cause or, thing that makes something happen. And so I was already used and it looks like a 1 anyway, but people were starting to think about imaginary numbers. They didn't want to use I, and then M was already mass. We had that there. It'd be really awkward if we had like M equals some other M. No, we don't like that. And then the next letter was P, so they went with P. So it's kind of like third pick there into what we end up with. Momentum has units of mass times velocity. So units of mass we know are kilograms. Velocities have units of meters per second. And when we put these all together, we call it a kilogram meter per second. It doesn't have a special name. If you want to call it a Daki, you're welcome to do that. But, people probably won't know what you're talking about. So we just call it a kilogram meters per second. It's a mouthful. It unfortunately doesn't get a special name. But if we were to report a momentum, we would call it a kilogram meter per second, a mass unit times a velocity unit. Momentum is the thing that's conserved in a collision. So if we can figure out how much momentum we have before in a collision, we can use that to show that the amount we end up with is that same amount. So the idea is if momentum is conserved, the total amount of momentum our system has is equal to the total amount after. So this would be like before, subscripts upon subscripts here, and then after. You figure out how fast your cars are going before and what their masses are. You think about how fast they're going after, and whatever happens before has to equal whatever happens after. We'll show you how to set that up next time. Now we're just going to kind of think in broad strokes what momentum is and how we can think about it. When we look at this derivation we did with Newton's laws earlier, we see we don't have mv proper, but we have m delta v. So for car 1, for example, we have mv final, that's, delta is a change in something, minus mv initial 1. So really we're comparing how fast car 1 was going after the collision to how fast it was going before the collision, and we're doing the same thing for the other car, but it gets a negative sign. It's the one that lost its momentum. So we would write m2 v initial 2 minus m2 v final 2, just kind of expanding out those deltas we see over here. And so it's not really momentum is conserved, but what this equation is showing us is it's the change in momentum that is transferred. Object 1 gained some stuff, object 2 lost that same amount of stuff, and so all they're doing is trading it around. This change in momentum for the whole system should be 0, though each object individually did gain or lose momentum. So we have a special name for change in momentum, and that is called impulse. So change in momentum we give a special name is impulse. It's literally a change in p, or a change in mass times velocity. Usually mass is going to stay the same unless you're working in rocket scientist, in which you're shooting mass out your back end and losing it as the rocket dispels its fuel. But for most things colliding, each object's going to retain its mass. So usually we can kind of get around that and just look at the change in velocity of each object. Impulse is symbolized, it's another weird one, with J. So delta P is J. I think it's just that's kind of like a different way to write an I if you're being fancy. It's a whole plot point in the third Indiana Jones movie, but that's a whole other topic. So J is impulse, which we want to think of it as. And if we go back to how we originally derived this, we started out with the forces on each object. And so if we multiply the m delta v over t was our force, mass times acceleration. If we multiply both sides of this equation by the time of the collision, we get another way to write the impulse. So we can also think of impulse as force times time. This force here is usually the average force the objects exerted on each other. This time is specifically the time of the collision. For most real collisions, this time is very, very short. We're talking less than 1/10 of a second for something to smack into each other and change its velocity. So this time tends to be quite short. What does this relationship tell us? Well, it tells us why airbags are good, or why certain safety features in a car do the things they're supposed to do. If we have a car and we're going at 60 miles per hour, that's our initial velocity. We crash. And no matter how that crash happens, the crash brings the car to a halt and we end up at rest. We start at 60, we end up at 0. There's no way around that. And so our impulse, J, is going to be based off that change in momentum. We have the mass of the car, V final minus mv initial. V final is just 0, so our momentum decreased. We went from some large speed to nothing, and so we lost momentum in that collision, equal to negative mass times the initial speed we're going, 60 miles per hour. But even though we always have this impulse, so this is impulse regardless of how collision happened. Things can happen in that collision to change the outcome for the driver, hopefully for the better. And the way we can do that is by looking at this second definition here. We've already used this first one. Impulse is the change in momentum, gets us this negative mvi. But that same mvi, this is a constant now, is equal to the force times time. Well, what does an airbag do? The airbag makes you hit a large cushion, which is going to increase the time of the collision. So if this is a constant, no matter how the collision is happening, if I can have an airbag that increases the time of the collision, larger time, well, larger time to keep this constant means that the average force you experience has to go down. And that's the key. The airbag provides a cushion, but what the cushion's really doing is it's increasing the time it takes to collide. For the same impulse, you're going from 60 to 0. That means that there necessarily must be less force exerted on the driver. And it still might be a lot of force, but it's certainly much less force than smacking right into the steering column. That cushion is good. An airbag is a cushion. A seatbelt is going to work to increase the time. Modern cars include crumple zones. They don't just, they take safety over durability, where the car is actually designed to change its shape upon collision to increase the amount of time, to reduce the force. That's all a cushion is. You're taking more time to reduce the force. So you can ask the same question. An egg on concrete, and then we have a nice cushion, fluffy pillow. We drop from the same height, h, an egg. The eggs are identical. They have the same mass. They're both dropped from rest. They're falling from the same height. So by conservation of energy, right before they hit their respective surfaces, they're going to have the same final velocities. So same gravitational potential energy means they're going to have the same kinetic energy right before collision. Now the concrete egg, we're going to end up with sunny side up when that hits, because the concrete is not going to give. The time of that collision is going to be very, very short. Whereas this egg is going to hit the ground. It's going to be cushioned gracefully. It's going to go boom, it's going to hit the cushion, and the time it's going to take is going to be relatively longer, meaning the egg, instead of hitting a nice smack to finish it off, is going to get the loving caress of the cushion, and it's going to survive the collision. So if you want to increase your chances of not getting hurt in a collision of some sort, do whatever you can to increase that time. Boxers will actually do something where they ride out the punch. They get hit, instead of ramming their head into the path of the punch, they're going to get hit, but they're going to move their neck back to go with it, increasing that time of collision and reducing the damage from the blow. So hopefully we're starting to get an impulse. Here's the final challenge here. It's another silly example where we have, for some reason, a pumpkin hanging from a rope. And for some reason, we're cosplaying as Hawkeye here, and we're going to shoot different kinds of arrows at the pumpkin. And we want to ask which arrow will cause the pumpkin to swing the highest. We have 3 arrows in our arsenal here. We have one arrow, which has this big balloon on the end. And it's designed to bounce off. We have another arrow that is, when it impacts the pumpkin, these spikes are going to launch out and it's going to lodge itself into the pumpkin. And then we have this super sleek arrow that's like a needle, and it's going to go right through the pumpkin with minimal resistance and pop right out the other side. And again, we want to know, based off these 3, which one is going to make the pumpkin go the highest. Take a moment to think about it to yourself. I'll go get a snack while you're waiting. And pause the video. Now, I'm sure you actually did that, and so hopefully you've come up with the right answer, and hopefully you have correctly picked that it is in fact the balloon arrow. That is the winner. The reason that this is due to the definition of impulse as a change in momentum. It has nothing to do with the fact that, it seems like it's a cushion here or something like that. We don't actually know anything about the forces or the times. All we know is that this bounces off, this lodges in, and this goes right through. We want to think about impulse as a change in momentum. It's the winner because it has the largest change in P. The largest impulse. Let's look at the needle, for example. Well, usually when I do this, nobody picks the needle. It's pretty clear that, the needle's not going to make the pumpkin fly up if the needle's going to go right through. Well, if we think about the initial velocity, all the arrows are shot with the same speed. If we're going right through, here's 0. We can imagine, the initial speed, not the final speed. Arrows comes in at some initial speed. It hits the pumpkin and it escapes the pumpkin going at some final speed. It's really sleek, so the final speed is pretty close to where we started. So this change in momentum here, delta V, is small. Well, now, so this was needle. Let's examine spikes. Same initial velocity. The spike arrow is going to, basically stop in the pumpkin, but it's still going to have some residual velocity left over that will carry it along with the pumpkin. It's not going to be as fast as the needle one is going. It's going to be somewhere closer to 0, but it will be the final. So now we have this change in momentum. It's sizable. Well, the balloon arrow bounces off. So what does that mean? That means we go from our initial velocity over here. The arrow bounces off and goes the other direction. So it actually jumps over into the negatives. Which means if I was going one way and the forces were exerted such that I went going the other way, that means my change in momentum was very large because I had to go all the way to 0 and then some back the other way. So in general, the moral of the story is here, change in direction gives largest impulse. If you're comparing a set of collisions and one of them involves a change in direction, you should characterize that one as having the largest impulse, the largest change in momentum. Since the balloon arrow has the largest change in momentum, when it collides with the pumpkin, it's also going to give that same large change in momentum, that same large impulse to the pumpkin itself, which is going to set this thing moving from rest to some significant speed, allowing it to swing up to the highest height it can. So the key here is not to think about forces and times. The key is to think about initial velocity versus final velocity. How big was that change? How much did I slow down? If I slow down a lot, I'm going to impart a lot of momentum. If I slow down enough that I actually change direction upon impact, I'm going to impart even more momentum than that. So there's your crash course on momentum and impulse. Pun was definitely intended. It's a thing I do. Hope you found this helpful, and thanks for sticking around.